So today I wanted to talk about solving recurrences. And again, let's look back at the Fibonacci sequence. So 0, 1, 1, 2, 3, 5, and so on and so forth. So the first term here, let's call it A0 equals 0, and the second term, A1 equals 1. Now we already know that the nth term of the Fibonacci sequence, Fn, well I guess we're using A, so let's say An equals A of n minus 1 plus A sub n minus 2. But here's the kind of fascinating thing. You might ask, well, is there a closed form expression in n that can generate the nth Fibonacci number? And it turns out that the nth Fibonacci number equals the following somewhat strange looking expression: 1 over the square root of 5 of 1 plus root 5 over 2 to the nth power minus 1 over the square root of 5 times 1 minus square root of 5 over 2 to the nth power. So this enormous expression here involving the square root of 5 of all things will generate the nth Fibonacci number. It's very interesting. So if you put n equals 0 here, you'll get 0. If you put n equals 1 in this expression and you simplify it, you'll get 1. If you put n equals 2, you'll get 1. If you put n equals 3, you'll get 2, and so on and so forth. And what I'd like to do in this module is show you how you yourself can mechanically come up with solutions to linear recurrences of this form. So the way it goes is this. I'll do an example and then we'll talk about the general case. So you take your recurrence, which in our case is A of n equals A of n minus 1 plus A of n minus 2. And of course we have our two initial conditions. Remember, for a recurrence like this, because it's an equals an minus 1 plus an minus 2, we're going to need two initial conditions. You form the following polynomial. This is called the characteristic polynomial. So in this case, this becomes r. This sort of corresponds to r squared. This corresponds to r, and this corresponds to 1. So r to squared, r to the first power, and this term becomes 1. And we get, if we were to subtract off these to the left, we'd get that r squared minus r minus 1 equals 0. So this is called the characteristic polynomial for this recurrence. Now we're going to solve for r. How do we solve for r? We use the quadratic formula. So what is the quadratic formula? It says that all the roots to this equation are, let's see, the opposite of b, where b is the coefficient here, plus or minus the square root of b squared minus 4ac over 2a. So what is b here? B is minus 1. C is minus 1, and A is 1. Okay, so plugging it into our formula, our quadratic formula, we see that the roots here are 1 plus or minus the square root of 1 minus 4 times A times C. See, 4 times A is 4, times C is minus 4, so this is going to be plus 4 over 2A, which is 2. So we're going to get, our two roots are going to be 1 plus the square root of 5 over 2, and our other root is going to be, so root 1 is going to be 1 plus the square root of 5 over 2, and root 2 will be 1 minus the square root of 5 over 2. So now you're starting to see where that square root of 5 came into play here. It came from the quadratic formula. Once we solved for the roots of this particular polynomial, we're going to know that, or it turns out that a sub n is going to be equal to some constant alpha 1 times the first root 1 plus the square root of 5 over 2 to the n plus some other constant beta 1 times 1 minus the square root of 5 over 2 raised to the n. And actually, I don't know why I used alpha 1 and beta 1. I'm just going to rewrite this as alpha times 1 plus root 5 over 2 to the n plus beta times 1 minus root 5 over 2 to the n. So this is going to be, it turns out this is going to be the solution to our recurrence. It's going to be some number times the first root to the n plus some other number times the second root raised to the power n. And the only question is, how do we solve for these coefficients alpha and beta? And we can use the initial conditions. So we know that a0, which is 0, so a0, which is the first term of the sequence, which is 0, is going to be equal to alpha times 1 plus the square root of 5 over 2 raised to the 0, because we've chosen n to be 0, plus beta times 1 minus root 5 over 2 to the 0. Now anything to the 0th power is 1, so this implies that 0 equals alpha plus beta. Okay, that's good. Now we can use the other initial condition, a1 equals 1. This is going to be equal to alpha times 1 plus the square root of 5 over 2 raised to the 1 power plus beta raised to the 1 minus square root of 5 over 2 raised to the first power. Okay, so now we have two equations and two unknowns. Just move this up. We're pretty much done. We have that alpha equals minus beta. That came from this equation. And then we have 1 equals alpha times 1 plus root 5 over 2 plus beta times 1 minus root 5 over 2. So we're really just taking two equations and two unknowns and solving them. So it looks a little bit messy, but it's actually fairly simple. So we know alpha equals minus beta. So we'll substitute in minus beta for alpha up here, and we get 1 equals minus beta times 1 plus root 5 over 2 plus beta times 1 minus root 5 over 2. Now we'll factor out the beta. 1 equals minus 1 times 1 plus root 5 over 2 plus 1 minus root 5 over 2, all of this times beta. So if you simplify what's inside this particular expression, you'll get, well, let's do it. So 1 minus root 5 minus 1 minus root 5 all over 2 times beta. If this step bothers you, just pause the video and write it out. It's just simplifying these two kind of arithmetic expressions. And so then we get 1 equals, let's see, minus root 5 times beta. And this implies beta equals 1 divided by minus 1 divided by the square root of 5. And since we said that alpha equals minus beta up here, this implies that alpha equals positive 1 over the square root of 5. Okay, so we've solved for our coefficients. Beta equals minus 1 over the square root of 5, alpha equals 1 over the square root of 5. And those are exactly the coefficients that we were looking for. Remember, I said earlier that the Fibonacci sequence was generated by 1 over root 5. Here's our alpha. This is the first root of the characteristic polynomial. Here's our beta, and this is the second root of the characteristic polynomial.